Okay. Let's continue with variation inference. So I would like to, at the beginning of today's lecture, finish what we discussed yesterday. These were techniques for parameter inference with variation inference, and the things that we didn't have much time for was a brief discussion about how to actually parameterize in a flexible way these probability distributions, the variational, which we called Q phi of Z. So this was the thing that we tried to fit against the posterior. And the only example that we actually had during the lecture was just a Gaussian, which is very trivial. An example that you actually have in the notebook is related to normalizing flows. So I want to just briefly mention how what's the main idea behind them. There would be much more to say. And then I want to briefly mention how variational autoencoders are built on elbow maximization. So they are essentially a small extension or small modification of what we discussed. And then the rest of the lecture will be about simulation-based inference, which is essentially a set of algorithms that one arrives at if one, again, starts with a KL divergence, but not from Q to P, but from P to Q. And this leads to a whole set of different algorithms with different properties. Okay. So first thing is variational distributions. So how can we parameterize in a flexible way a probability distribution that is normalized to 1? And on top of that, as we saw for calculating the elbow, we actually also need the entropy, information about the entropy of this function. And so just taking any arbitrary neural net wouldn't work because it's neither normalized to 1 nor it's non-negative. And we in general will not know what the entropy is. So the basic idea of a normalizing flow is now to start out with something that is simple, let's say Gaussian. So I just, it's a standard normal Gaussian in some high-dimensional space, and then apply some transformation. And this transformation is learnable, so it has some parameters phi, and it's invertible. And we know the Jacobian determinant. So we have then a transformation like this, which might turn a distribution that looks Gaussian to something that might be multimodal and very non-Gaussian. And this here are, let's say, this is just a two-dimensional example. Good, and now a question is how could we actually set up transformations like that? So the basic idea is, so we want to have this invertible transformation for which we know the Jacobian determinant. And instead of, and we build it up from, out of simple building blocks. So instead of having just one transformation, we have a whole series of them. Let's say L. And if we know if we have one simple transformation that is invertible, and for which we know the Jacobian determinant, if we just stack them, they are still invertible, and we just multiply the determinants, and we are happy. So that works well. And so one of the constructions that is very popular is now what's called a fine coupling layer. And what I'm going to describe will sound very specific, but it's actually an underlying trick that underlies many algorithms. And you will see how it works in a second. So the idea is the following. So we're interested in building a transformation. And let's say we have some input, vector z. Then the first step is to split this up in parts that we call P for passive and A for active. And how to do the splitting will be very context dependent. For instance, you could just take half the pixels of an image as active and the other half as passive, and then it could be the left side of versus the right, or alternating pixels, or whatever you want. But the basic idea is we split the vector up, and then we want to map it on some output. And the trick is now to keep the passive part unchanged. So the output will be afterwards concatenated and just be the output. But we use this passive part to now modify the active part. But we modify the active part in a linear way. So that's essentially the idea. So what this does is we have now, so P comes in, the passive part. It has now a nonlinear mapping on some matrix. And this mapping can be nonlinear. So it can be parameterized by a neural net. Let me put a little neural net here. And also, this determines the bias vector, which again can be nonlinear. But then the mapping for A is actually linear. Okay, and this looks like a weird choice. But the reason why that's interesting is twofold. So first, if we can go in that direction and want to go back, the advantage is that we already know, so if we want to go from here to here, we know the value of P that was used to go from A to A prime. So in general, we can invert this and go. So once we know P, we can calculate W and B and can go from A prime back to A. So it's invertible. Yep. Okay, so what I want to say is that these are matrices which are nonlinear functions of P. So at some point, there will be phi playing a role which parameterizes a neural net that does the nonlinear mapping. So in the notebook example, actually the matrix, so W is just 1. I kept it constant, or I kept it 1. And there's only this bias. And this bias is simply a function of the other parameter.
Also, the weight and the bias depend on I, right?
The weight and the bias, they depend on I. So for each layer, you would have a different set of mappings. And also the splitting depends on I. So all of that depends on I. Good, so now the reason why that's interesting is because now if we look actually at the Jacobian from out versus in, and I'm now writing this in a with block matrices, then there will be a part that comes from taking the derivative of P with respect to P. So this will be just the unit matrix. Then there is a part that comes from taking the derivative of A prime with respect to A. This will just be our matrix, which will depend on P. And then there is this part here, which will depend on P, taking the derivative of P with respect to A. This will be just 0. And here we will get a complicated mess. So here, this will be a derivative of A with respect to P. But the interesting thing is that if we calculate the determinant, we don't actually know that part. Don't need to know that part because on that side it's 0. So it's a triangular matrix. And so we only need to take into account the diagonal elements. And this here is 1. So we only need the determinant of W. So the entire determinant of the transformation becomes just the determinant of this matrix here. And depending on how one sets things up, that's very solvable. And so in the simplest cases, one would keep this here, just like keep this as a diagonal matrix. And I mean, then all this is very simple to evaluate. In the example that you have, as I said, actually the matrix is set to 1. So there's no rescaling happening. And only B matters. And as a result, all the determinants are 1. And as a result, we can calculate the entropy just by calculating the entropy of the distribution that we started with. And you see this in the code. So when I calculate the entropy, I just calculate the entropy of the distribution we start with. OK, so that's everything I want to do about this. It's kind of a neat trick that one encounters over and over again in context of building machine learning algorithms. So just building transformations for which you can get easy determinant calculations by keeping part of the Jacobian 0. And then you can make quicker, or yeah, then things are easy to calculate. So this is called a fine coupling layer. Question? Yeah?
Could you explain the entropy? Why it's the same?
Basically, you can write down the entropy in terms of Q, and then reparameterize, and then so to actually take the integral in the end over the z's you started with. So where are the z's? So z input, not that output. And then if you set everything up such that the determinants are 1, case, the cancels. Usually, you actually have to take into account this effect here. So the usual ways you start out with the standard normal distribution and don't modify it, but then you keep track of all the determinants of the Jacobians. In my case, I was a bit lazy, so I just changed the initial distribution and then keep the determinants 1.
And if you determinants are from 1, the entropy increases, or well, it's modified by the determinant.
Yeah, yeah. Yes. Good. So next thing is connection with variational autoencoders. Good. So here the idea is the following. So when we train the elbow, let me write down the full thing. What we did was we optimized the model for some for Q, right? So we wanted to turn Q into a posterior. And we did this only for one particular observation. So we didn't care about making this work for many observations at the same time. But let's now write more explicitly that actually Q could be also a function of the observation itself. So if you apply the algorithm simultaneously to multiple observations. So then what we can do is, for the typical terms that appear in the elbow would be the likelihood function, the prior, and the entropy of the variational distribution. And what we could now in principle do is to say, OK, actually, we want to train the model for multiple observations at the same time. So rather than just plugging in one specific observation for x, we could sample from many possible observations. OK? And they are here in this distribution Q. So this here might be now simulated observations, or this might be also real observations. And then the entire elbow will be still something that we would maximize, but we would also randomize over x over the observations. And then the variational distribution that we just wrote down there would actually turn into something that depends on whatever observation we plug in. So if you think about this variational distribution, the logic would be that the neural nets that we here learn to parameterize, for instance, the weights and biases themselves, depend not only on the weight, but also take as input the observation x. OK, so and then this function would actually turn into kind of inference machine, which isn't just posterior for a specific observation, but it's a neural net that can tell you the posterior for any observation that you plug in. I mean, provided that it was properly trained on it. So that's in general something that works for elbow. It will be also something that we see for simulation-based inference. But what one can do then is the following. So one can build variation autoencoders. First, draw something to visualize the idea. So variational autoencoder is basically the following. So it's an autoencoder which takes as input some piece of data X that might be an image. So most typical examples, also the one that you will work on in the notebook, are images drawn from some distribution, from training data distribution. And then the idea of an autoencoder is to find an embedding of this high-dimensional object. So X would be high-dimensional. Right, so if it's an image, it's just all the number of pixels that you have in the image. So find an embedding via this encoder into some low-dimensional parameter space or latent space. So for instance, we would try to take like high-resolution images and compress them into like a vector with 10 components. And we want to compress it such that we can feed the vector into a decoder, which then can reconstruct the original image. So this would lead to a reconstructed image. So that's, in general, the idea of an autoencoder, so to find low-dimensional embeddings of data that we have. And now this connects directly to what we discussed in the following. So we could interpret this part of going from X to some internal embedding as our posterior. Right? So the posterior would just tell us, the variational posterior, what are the most proper parameters that would have led to that observation. And then we have also the generative model or the likelihood model that then goes back from the parameters to the actual observation. Okay, so the idea of a variational autoencoder is now that given a large number of training images, we can try to learn not only the part that tells us how the images map onto the parameters that produce the images, but we can also try to learn the decoder, so the model that goes back from the parameters to the images themselves. In the examples that we had yesterday and that you had in the homework, in the tutorials, P of X given Z was actually a physics simulator, right? So this thing that was throwing balls. But in principle, you could parameterize this also as a neural net that goes from 10D to 100D. And typically, this would be a deconvolutional neural net or something that depends on context, but a learnable deep neural net. And so the idea is now of a variational autoencoder that to use elbow maximization to train both these model components at the same time. So instead of just maximizing the elbow with respect to the encoder part, to the posterior part, we also would maximize it with respect to the likelihood part itself. And good, so that's the idea of a variational autoencoder. Typically, now in practice and in the first versions of this that existed, all of this would be parameterized as Gaussians. So you will say there's a Gaussian prior for the latent space parameters. Sorry, this is latent space parameters. There's a Gaussian. You also assume that the variational posterior is simply Gaussian. And you assume that the model predictions are Gaussian. So all of these components, the network here would essentially just predict the mean value of a Gaussian. So it would predict an image. And this encoder network would predict the mean and variance of the posterior for the individual latent space parameters. Good. So the idea is pretty general. You will see in the notebook a concrete application where the entire model is simply trained on handwritten digits, on endless data, which is like the most typical, I guess, starting point for training any neural network. And the model will then figure out how to take digits of 3 and 1 and so on and embed them in a latent space so that afterwards, from this latent space, you can get original images back. And there are many applications for this. So the traditional applications for this have been like generative models. After training a variational autoencoder, you can just sample new parameters from the prior here and get new numbers. And you will see this kind of works. You get 3s and 1s, but also sometimes mixtures between various numbers. Yeah, but the basic idea works. Nowadays, there are much better models for generating images. For instance, you would use diffusion models But knowing this kind of logic and album maximization will also help to understand these more advanced models, because the basic ideas that you see here will reappear over and over again there. Are there questions about this? Mm-hmm.
So this P of theta, isn't it possible to determine that from Q of theta by inverting it?
In principle, yes, but I mean, not only formally. So you could, of course, write. Yep. Sorry. So the question is, couldn't you reconstruct Q from P or vice versa, right?
Or P from Q.
P from Q. Yeah, not directly, right? So they are two sides of the story, but they are not. So if you have Q, this will be typically a network that takes a high-dimensional object and compresses it to something low-dimensional. This doesn't mean you can directly invert the network computationally to get back to the input. Is this the question?
You have to add some free parameters, like let's see, I forgot what the free components of a non-invertible matrix. You'll have to add something like that, but other than that, it should be possible to invert every step. There might be some weird conditions where it can't invert for like the rectilinear. If it's negative, that it can't invert. You could keep selecting random free degrees of freedom until it is valid.
I'm not entirely sure. So even if so let's suppose you know perfectly P of X given Z, and you know perfectly P of Z given X. The way they are related is via Bayes' theorem, right? So this is what connects them. But knowing these two quantities doesn't mean you know this and this. So even if you know this here perfectly, you can't automatically invert it fully. I mean, they are completely different objects, but this is more a statement about whether, in principle, it could be possible to recover the full information from, if you know one perfectly, could you recover from the information that you have about the one, the other? And I don't think that's the case. Although I haven't thought this entirely through, but I think this would be a problem. Yeah. So the idea why Gaussians are used is because were used traditionally as like starting point when this model was first proposed, which is 8 years ago maybe, by Kingma and Welling and others. It's simplicity because yeah, it makes life easy. So this model here would essentially just predict the mean. So this would be just a Gaussian that predicts the mean value, and you assume specific variance for the uncertainty on that side. And this will turn into mean square error loss function. And here for the priors, you will get a Gaussian, so that's easy, and if you write the log of it. And here you would also use Gaussians, because then you only have to predict the mean and variances of the output. There was one question, actually, how one would get from a Gaussian to the chi-square loss function. And right, so if you start with a Gaussian, right, you have something of that form with some prefactor, and if you take the log of that -2, you end up automatically at the chi-square, up to some normalizing factor, which in practice, in many examples that people that you will find in the literature, these factors are just set to 1. Or it's assumed that sigma is the same for all pixels, and then it's over a rescaling factor that you can just set to 1. OK, so this was just something that I wanted to add, because otherwise you will not know much what's going on in the homework. But I would like to go to simulation-based inference now. Or not homework, in the tutorials, I should say. So let me talk about SBI. And And I think this is right, part 3. Right, and I wanted to start with like an general overview of like sampling versus evaluation. Okay, so we talk all the time about the likelihood function, right? And so that's like the likelihood function for data given some model parameters. And there can be, we can do a few things with the likelihood function. We can sample from it, right? And in that case, what we need computationally is a simulation program, which takes as input some parameters, and then it runs, and it returns a sample of X. And if you run it a second time with the same parameters, we will get a different sample. So if you want to sample from the likelihood, we need a computer code that does that. Then we can also try to evaluate it, right? In that case, we need a different piece of computer code that takes as input the parameter and some specific observation X and returns the log likelihood, right? So that's in some sense doing the same thing, right? It's in some sense doing something with the same underlying distribution. But these are generally 2 different pieces of computer codes that you have to write. And okay, there are probabilistic programming languages that automatize this. But in general, you either write something like this or like this. And if you have 2 computer codes, one does this and the other does that, it's very difficult to tell that they actually talk about the same underlying distribution. And then you could do something like evaluating the score, right? So you could be interested in the derivative of the log likelihood with respect to the parameters, let's say. So this here would be yet another piece of computer code that would take as input some observation and some parameter z, and in this case, it would return the score function, so the derivative of the log likelihood, which actually is a vector, right? Here the return value is a simulation. This might be an image or like collider track information, so a list of particles. This here is a single number. This here is a vector of numbers. And now, depending on what piece of code you have, you can run different algorithms. So if you know how to do the log likelihood evaluation, you could run Hamiltonian. You could run Metropolis-Hastings algorithm, some MCMC algorithm. If you want to run Hamiltonian Monte Carlo, you would need evaluation of the log likelihood, but also of the score function. And then there are techniques that only rely on the score function. Then when we talked about VI, variational inference, when we look at the elbow and want to maximize it, we actually need to evaluate the likelihood, and we need to evaluate the score of the likelihood function. Okay, so these are things that we need to calculate. Now, when we talk about SBI, that's actually an algorithm or a set of algorithms that lets us get away with not having code to calculate the log likelihood function or the score, but only to have samples. The samples would be pretty useless for running MCMC or Hamiltonian Monte Carlos, but they are the ingredient for simulation-based inference. That's why it's called simulation-based inference, because it's based on these kind of simulation results. And there's a whole range of algorithms like neural posterior estimation, neural ratio estimation. Also, similar algorithms are invented multiple times under different names. So it's also a bit confusing sometimes to understand the literature if you just start it. But I want to highlight here the most common approaches maybe that are mostly used in the context of physics, I would say. Right, and the traditional version of SBI that is around since the 80s is approximate Bayesian computation. So in the same way, chi-square is related to elbow maximization, approximate Bayesian computation is related to this story. So who knows approximate Bayesian computation? Who has heard about this? Who has heard about approximate Bayesian computation? Okay. It's very unpopular because it's difficult to use if you can't train a neural net. And so I want to first tell you a bit about approximate Bayesian computation. and show you how it works, and then explain why it's difficult to use it, and then why having a neural net that you can train automatize doing that. And it's useful to think about approximate Bayesian computation as a starting point, because all the intuition that you can get from thinking about ABC will also translate over to how simulation-based inference works in general, or much of the intuition. So again, the idea is, let's suppose we have some simulator, right, which returns us mock simulations given some input parameters. And even if, as I said, even if you keep the input parameters fixed, each time you would get a slightly different simulation, not the least because there might be different measurement noise. Yeah?
I would expect Markov chain Monte Carlo comes from simulating the system. Maybe I'm misunderstanding what.
Yeah, that's very good.
Can you clarify?
Yeah, thanks for the question.
Just imagining, like, I don't know, you're just doing like an Ising model. Like,
yeah.
How is it that you're not just.
Yeah, I will repeat the question. So the question is, and it's a very good one, thanks for asking it. What's actually, I mean, even if you run a simulator, right? Or if you run a simulator, typically you have to run a physics simulation at some point. So you have to simulate what you expected to see. And you typically need to do this both for evaluating log likelihood functions as well as running a simulator. So the question is how this actually connects and why a simulator doesn't seem to be necessary for Markov chain Monte Carlo. So one simple example would be think just about like this kind of data point. So just a linear regression example again, where we want to fit some line to data that we have. Then we can say the underlying likelihood model might be, as usual, just a normal distribution with some mean values that depend on Z, and then some measurement noise, which might be also depending on Z, but let's say it doesn't. Then all the physics simulations actually typically go into this, so into calculating the expectation values, because this tells you like the actual, let's say, physical cosmic ray flux or whatever you measure there, or the physical expectation values per bin in a collider experiments if you have specific observable. So you need to run a physics simulation to actually get these expectation values that you need as input to calculate the log likelihood. So it's part of that. If you run a simulator, you would also do this. So you would have to calculate this number, but then you would add some measurement noise. And this would return X. So this here would be the deterministic part of the simulator, given Z. And this here would be the non-deterministic part that changes each time when you run the simulator. Now things can become a bit tricky, because you can just say, OK, but now I just treat one of these parameters here also as non-deterministic. And when, each time when I run the simulator, let's say the simulator here depends on Z1, Z2, Z3, right? So something like this, plus the measurement noise. Then you could write a simulator that depends on Z1, Z2, Z3. And then each time when you run the simulator, you would just resimulate the noise. But you could also say there's a simulator that just depends on Z1 and Z2. And each time when you run the simulator, you also randomize over Z2. So Z2 would be also drawn from some distribution. So in some sense, what I want to get at is that the notion about what's random and what's not random in a simulator depends a bit on what you hide inside the simulator and what you keep as external parameters. Even if you have a simulation code like this here, which returns random results each time, so with randomized measurement noise, you could also have the measurement noise externally fixed. So this would be like, instead of sampling from this distribution, you would sample from something where you also pretend you know how the noise looks like. Then you would always get the same answer out of this, if you keep the noise fixed and the parameters. Does this help? So the simple part is either you take the physics simulation and calculate this likelihood function and get a value out of that, right? By plugging in the simulation here and the physics simulation result here. No, sorry, the data that you measured here, the physics simulation result here, and evaluate this, and you get a single number. Or you take your you take your simulation result, add measurement noise, and then you get mock simulations. So these are two different things one can do. And in many cases, it's easier to write a simulator like this here rather than to write a likelihood function that would describe how the data is distributed. Here it's very simple because we just take our physics simulation result and add Gaussian noise, so we end up with a likelihood function. But you can imagine to add here all kinds of complicated stuff that you simulate that is just outcome of your like Fortran code. Then it would be very difficult often to write down explicitly likelihood function, probability distribution for how the output is distributed. And so often this here is more general, but this here is more prevalent in many contexts. So if you analyze cosmological data, you wouldn't analyze simulated data. You typically analyze likelihood functions. Or your analysis is based on the availability of likelihood functions. Is this roughly clear? OK, I will explain you a bit how ABC works, and then you will see what are the ingredients into approximate Bayesian computation. And that they are quite different from a chi-square fit. I mean, we discussed chi-square fits yesterday. What I will now talk about will look very different. So if you do ABC, you would first simulate and get simulation data. By running, by drawing many times from your prior, and then running your simulation code many times accordingly. In this way, you get like pairs of mock data and parameters. And then what you can do is you just, if everything is low dimensional at least, or if the parameter is one dimensional and if the observations are low dimensional, we can just put all the simulation results in the plane, right? And in one case, we might have sampled this value for Z, right? And then we put this in the simulator, and we end up with the result here. And then we repeat, we might sample this value for Z. We get something here. And then we keep repeating until we got a larger number of simulation results, okay? And good, so that's something that you can do when you have a simulation code. This is nothing that you can do when you just have a code that gives you evaluations of likelihoods. Good, so now how can we use this for getting posteriors, right? So now let's assume we actually observe a specific value for x, right? So let's say this is our observable. And what we are interested in is now how to get samples from the posterior. How to sample. Okay, and the way to do this with approximate Bayesian computation, and it's really just exploiting the logic of conditional probability distributions. So the way you would do this with approximate Bayesian computation is you, in this case here, just look at the simulation results that ended up close to the observed value within some small range. Let's call this 2 epsilon. Okay. And you disregard the rest. So you just, from all the simulations that you might have run, let's say 1 million, you keep only the 10,000 or the thousands that happen to lead to observation that is very close to what you observed, okay? And then you take those samples, right, and put them in a new histogram. So again, a function of Z. And we now focus on the samples that we have from this region here, right? And put them here in a histogram. And this will then, if one smooths it nicely, will look like something like this here. And this here will be an approximation to the actual true posterior. So it's an approximation because what we actually sample is not the probability distribution of the parameters given the observation, but it's the probability distribution of parameters given that the observation is close to x. Okay, so it's a slightly weaker criterion. If we would let epsilon go to 0, we would get the correct posterior back, but then we wouldn't have any simulations left. So there's, in this context, a trade-off between how many simulations do you have to make your posterior versus how precise your posterior actually is. Okay, so that's the idea of approximate Bayesian computation. Questions about that? Yeah.
How do you pick a value of epsilon, like practically?
So usually, so I'm not advocating doing it exactly like this. It's just the very fundamental idea. In this context, you would simulate as much as you can afford computationally, and then after that, maybe take an epsilon so that you are left with, let's say, 3,000 simulations, so that you can get a reasonably neat posterior. I mean, if you have 3,000 simulations left, probably it's enough, or even if you have 100 left, it's enough to estimate like mean and variance of this thing. To get a smooth posterior, you typically would need far more simulations than a few hundred. It depends then on the context. But yeah, that's one of the drawbacks of this. And there are many extensions of this. So one way would now be to actually smooth the distribution of data points, right? So you could then do density estimation to the data points and then just evaluate this. Or you could do kernel density estimation based on the things that you selected with a small epsilon and so on and so forth. Good, but there are two challenges with this. So one is, as we just heard, the epsilon to 0 limit, right? And the other is, okay, this looks nice in 2D, but imagine now situation where the data isn't just one parameter, right? But where the data might be an image with 1,000 pixels, right? Then we have to somehow replace this simple statement here by something else, and then you could say, okay, you keep all the samples where whatever distance measure you can come up with between the observation and the simulations is small. But this becomes typically very inefficient because if you want to have a tight enough distance measure to get good posteriors, you typically end up with an acceptance rate of 0. Simply because in order to be accepted, if you make epsilon small enough, not only the model parameters have to be right, but also all the statistical fluctuations in all the pixels have to kind of nicely align with what you see in the actual observation for this to work. So what one would do instead is typically one would use data summaries. So instead of plugging x directly into a distance measure like this, you would hope that there is like a sufficient data summary that still contains all relevant information that you could ever wish about the parameter z. This can be low dimensional, and if it's low dimensional enough, you can in principle still use approximate Bayesian computation. So the reason why you probably haven't heard much about it and why you haven't used much of approximate Bayesian computation so far is because often it's very difficult to come up with good data summaries that you could use as input for an algorithm like this. And what simulation-based inference in some sense does, it's training neural networks to both generate sufficient or ideally sufficient data summaries, as well as training networks that help you to do the epsilon to 0 limit. Okay. There are a lot of aspects of approximate Bayesian computation which are quite nice conceptually, but I will come to that a bit later. So the nicest aspect is that you don't actually need a likelihood model. So you can have an arbitrarily complex simulator that has many, that has pieces of code that have stochasticity for which you don't have a likelihood model anymore. Good, so how to do this in practice? Well, so the probably most popular approach to this right now in the literature, at least in context of physics and astronomy applications, is what's called neural posterior estimation. And it's a very general term, but it refers to something reasonably specific and also a very specific algorithm. And depending on depending on the literature you read, there will be different words for it. But I explain you the algorithm, and then you see what I mean. Good. So the idea is, again, we want to have now a probability distribution, a variational distribution that we fit against the true posterior. I still say here variational distribution, although it's not variational inference, but the words are not that strictly defined in some contexts. So the starting point will be as it was before the KL divergence. But this time, it's the forward KL divergence. And what forward simply means is that we, instead of writing KL from Q to P, we write KL divergence from P to Q. So what we want to minimize is now KL from the true posterior to the variational posterior that we want to fit. And I can again write the definition in terms of samples. So this here would be evaluated by sampling from the true posterior, from our target posterior, and then we take the expectation value of the log ratio between the target posterior and the variational posterior. Okay, so this is our minimization objective. Well, it's not entirely our minimization objective yet, but it's the starting point. And yesterday, when we started to derive elbow, the only difference was Q was on this side and P was on that side. But that's a pretty fundamental difference, because now, before we had this challenge that we had here, or the situation was we had here to generate random samples from the function that we want to fit. Here this disappeared. Here the random samples are actually generated based on the posterior that we want to fit, so on the underlying true posterior. So all the weights that we want to optimize are actually inside the log here, which means we will not need the reparametrization trick anymore. But the problem is now, actually we don't know how to sample from the posterior in the first place, right? So we have here a starting point which is intractable as it stands. And right, so this here is something we can't really, or we don't want to sample from the posterior because this defeats the purpose. And then we have to run CMC or something like this. We also typically can't evaluate here the posterior density, because for this we typically will not have the normalization, or we might have not code to even calculate the likelihood density. So the only thing that we know to calculate how to, I don't have green. The only thing that we know how to calculate right now would be, or that we assume we know how to calculate, would be the variational posterior. So how can we solve that problem? Well, the idea is now, instead of solving this specific problem, we solve a somewhat more general problem. So instead of trying to solve variation or get a posterior just for one observation, we try to get posteriors for all possible observations. So it's in some sense similar to what we did here. We just take our optimization target and start averaging over many possible observations. So and if you do this, I mean, we can just formally do this, right? What happens is the following. So we get, where should I start? Yeah, OK. So we can write here now the expectation value of the KL divergence over samples from X, and combine this with this expectation value here of samples from the posterior. So I write it like this here, samples from the posterior, given this X, right? So, and then we still have this log ratio here. And I split this up in the posterior part, the true posterior, and then the target posterior. the variation posterior. Good, so now this is a slightly more general loss, right? So rather than just looking at the KL for a specific observation, we look at KL averaged over a wide range of observations, all drawn here from this from the Bayesian evidence. And now there are two things. So the first thing is this is going to be an optimization target, right? So terms that don't depend on phi actually don't matter. And this here is a term that doesn't depend on phi, so we can just forget about it. And then the second trick is what we do here is we sample from posterior times evidence, right? Which would be very difficult to do. We would have to solve many inference problems if you wanted to do it exactly like this. But thanks to Bayes' theorem, we can just rewrite this as samples from the generative model. It's the same thing. So instead of sampling first from Bayesian evidence and then solving and then getting a sample from the actual true posterior, we can first sample from the likelihood function, which we know how to do, plug this in our simulation model, and get a random simulation. So this part here is exactly the thing that we were doing here when we do approximate Bayesian computation. We just run the simulator many times for different draws from the prior. So now we suddenly have a loss function that solves a slightly more general problem than the one that we initially started with, but that has only tractable components. So we have here samples from our generative model, and we have here variational posterior that we want to fit. And that's the idea of neural posterior estimation, essentially. So as you can see, it's conceptually much easier, or maybe it's much easier than elbow maximization in the sense that there's only really one term to care about. We don't need a differentiable simulation code for the likelihood function. We just need to have a simulator that we can actually sample from. And that's about it. So next thing is I want to write down the algorithm, but yeah, I'm sure there are questions about this.
Does that mean that the conditional process more efficient here?
It depends really on the context, I would say. Right, sorry. So the question is, are the computational costs of this lower than of variational inference? This depends on the type of problem. So if you have here you inevitably have to train a neural net that can actually interpret the data, right? And it might be that the data is very complex. So imagine you have a very noisy, huge image, and you just want to measure, let's say, the flux of some astrophysical source in a specific region of that image, right? Then you need to train a neural net that can interpret that image and figure out where to extract the correct information and so on. Whereas if that situation would be such that the likelihood function would actually be easy to write down, right? So let's suppose you have just a flat background, one source, nothing magical happens. Then the likelihood function is something very simple. And then it's typically much easier to just do a chi-square fit, or maybe do something that looks a bit like variational inference if you want. So that there are circumstances under which this here is much easier or more efficient, and then there are circumstances under which that here can be more efficient. This year, SBI becomes more efficient if you are in situations where you don't have likelihood functions and where you have maybe very large number of parameters. And then it becomes very difficult sometimes to use this or impossible. Yeah, so it's good to know about both approaches, and they have their pros and cons. And there are also kind of hybrid things in the literature. More questions? Yeah. Yeah. I mean, in the limit where both perfectly works, you would get the same answers. Whether one is faster than the other really depends a lot on context, I would say. There is no easy answer. I think in cases where you already know how to get solutions based on the likelihoods. Typically, the advantage in some cases when you run SBI is that you can do it faster, because often doing things like this here actually is quite time consuming. So if you, the traditional similar likelihood-based way would be to run MCMC, which takes time. But this here can also, in practice, take a very long time because you have to. So in practice, this also works like a fit, which slowly has to approach the minimum and so on. So yeah, there are situations where where just likelihood-based techniques are very fast and efficient, and where it's probably better to just keep using them. Then there will be other situations where SBI is better. One situation where this here really struggles with is, I think, highly noisy data. So if you have data which is completely flooded by noise with millions of bins, but you have a very low-dimensional model, let's say, gravitational wave signal with 15 parameters, but 1 million or 1 billion of bins that you have to take into account, then SBI-type methods typically struggle more because they have to figure out how to extract this information from this very noisy data, whereas the likelihood function in some sense already knows that. So you can look at scores or something like this. So you can even do sometimes Fisher forecasting and get the right answers. So this can be, or use Fisher-type techniques to get the right answer. So this can be far more efficient depending on the context. But yeah, the easiest is to play a bit within practice. So you will today in the tutorial, you will actually find examples where we solve the same problem that we solved yesterday with VI with SBI. And you see it, you get the same answer, but it works differently. And I think it works a bit faster. You can play a bit around with this. Good. So I need to explain. How do I do this now? We have 15 minutes left. The algorithm that you actually have in the tutorial is not this one here, but it's neural ratio estimation, so I have to explain this as well. So maybe I tell you a bit about neural ratio estimation. Now you find the algorithm for this here in the notes. I mean, it's reasonably straightforward. You generate training data, and once you have this, you basically feed this through a neural network with this type of loss function. So loss function is minus ln neural network density. The big challenge, or not big challenge, but one of the challenges in using this type of approach based directly on the KL divergence in this way is that you still need a density estimator. So the network that you optimize here needs to be something normalized to 1, non-negative, and so on. So in order to do this here, you need something like a normalizing flow, or you assume that the posterior is Gaussian. And good, so I want to now also tell you about the algorithm that solves the same problem, but has less requirements on the network architectures. And it's also based on the KL divergence, but again, in a slightly different way. And it's called neural ratio estimation. And here the idea is, neural ratio estimation provides a way to do to perform inference tasks using energy-based models. So what is an energy-based model? This simply means we think about the density function that we want to fit as something that we can write as e to the power minus e. So that looks a bit like energy, but for us it's just a parameterization. And then we say, okay, we actually don't know the normalization, which you might want to call partition function. So as a physicist, you would call it maybe partition function, but here it's just the situation, okay, we know, or we want to model E. So we model this as a neural net. And we say, okay, we actually want to do it in such a way that we don't need to know the partition function. Or we don't need to know the normalization. So what you see here is if you parameterize a neural net in this way, or density function in this way, it's automatically non-negative, right? Because we have e to the power minus something. At the same time, E can be now any network So it can be just a multi-layer perceptron. So it's quite general. But what we need is an algorithm now that can deal with the fact that we don't have the normalization. And as I mentioned yesterday, when we introduced the KL divergence, what we actually need to show that the KL divergence is non-negative is that that whatever we plug into the KL divergence is normalized to 1. If we stop doing it, right, this just breaks apart. So if you have here a normalization that is not fixed, could just explode, and the loss goes to -infinity and or becomes very small, and that's it. So that wouldn't work. Now there's a whole range of interesting algorithms to optimize energy-based models, and there's a very nice paper by Kingma and others, also a couple of years old, which I think I put already on the Google Drive, otherwise I will still do it, about how to optimize your energy-based models. And there's like 5 different algorithms. Density ratio estimation is one of them in a different way. But good, so the idea is the following. So rather than trying to estimate the posterior density, which is distribution function normalized to 1, we try to estimate this ratio between the posterior and the prior. This is now just a function that is not normalized to anything anymore. It's not immediately clear that it's easier in the end, but that's now our goal. And as you can see, if you have this ratio here, which you might call x, z, if you have this ratio, and if you know what the prior is, we know the posterior, right? We just multiply it. Good, so now we can rewrite this. So if you multiply numerator with px, we get this here. So this is now the joint distribution divided by the marginal distribution. I will say in a second what that actually is, and then we can divide, if you want, by the prior on both sides, and we get this expression. So this here would be now likelihood to evidence. This is all the same, just different versions of writing the same thing. And now the idea is, okay, so now this here, what this here actually means is this is the joint model, right? So in order to generate samples from the joint model, what we would do is we would first sample the parameters, and then we would sample mock data. So if you sample from the joint model, we would end up with samples that look like these red dots here. So let me show this. So this would be a bunch of red dots. And this would be the joint model. And then we have the marginal model, which works like we sample a parameter somewhere, and then we sample independently from the parameter, we sample also an observation, which we can do by sampling yet another parameter and sampling observation for that, and then forgetting about the parameter that we used to sample that observation. And what we get in this way is basically the same distribution, but scrambled independently. So we would mix x and y parameters randomly. And so what we end up with is then a distribution that is all over the place, right? And now what we want to do is to train a neural net to solve a binary classification task, telling us whether, when we look at some point here in this parameter space, this here is z, this here is x, whether this belongs to class equals 0, so this would be the marginal distribution, or to class equal class 1, which would be the joint distribution. This looks a bit messy, but the logic is we try now to reformulate this problem here, the problem of learning this ratio as a problem of binary classification, which is something that we discussed already and that we already know how to solve. So in order to, yeah, I have enough time. In order to do that, we need to define now a little mixture model that we use as auxiliary model. we introduce a new model that now depends on the data, and it depends on the parameters, and it depends on the class parameter y. And we set it up such that that it equals, so for y equal 1, it equals the joint distribution for parameters and observations, and otherwise it equals the marginal distribution. Okay, so it's just like what we just defined a model with two classes, right? So one is parameters and data are correlated, in the other case they are not correlated. And now, what we typically assume, but one can also assume something else, but for simplicity, is that the priors for both classes are the same. So if we sample from this model, half of the samples would be joint, and the other half would be marginal. And the nice thing is now when we look at least formally now, at the posterior for a class, for a data parameter pair to belong to class 1, then that posterior will be given by px, pz divided by joint distribution. So joint distribution divided by joint plus marginal distribution. Okay, and you can already see that if we now divide by the marginal distribution, we get the ratio, right? We get r divided by 1 plus r. So it's kind of hidden in there. Good, so the next step is then to write down the loss function for this. Right. So the loss function is now exactly the same loss that we had before when we were talking about binary classification. So we have one part that corresponds to samples from class 1. And then here, the log of sigmoid of output of some network. And as input, it takes data and parameters. And then we have one part that is based on samples from the marginal distribution. And here we have, again, log of sigmoid of minus f now. Okay, so this is just the binary cross-entropy loss function that we used already for logistic regression. So it's the very same thing, except now that the distribution of the two classes looks like this here. So it's for class 1, it's joint distribution. For class 0, it's the marginal distribution. And what one can now show is that if one minimizes this loss, then the network starts to approximate the log of the ratio that we are interested in. So let me write this explicitly again. And a nice exercise is actually to show this explicitly if you want. So if you want to, I mean, first this falls kind of from the logic of the Bayesian problem that we are solving, but it's a nice exercise also for the elbow in the end. You can simply replace these expectation values by the integral expressions on that side and that side, and then take a functional derivative so with respect to f. So you and if you set this to 0, then that's the solution. So what this essentially tells you is that if you minimize the loss, and then in the limit of a infinitely flexible fitting function, which is your neural net, and infinite training data, where you can actually replace these expectation values with integrals, you get exactly the correct answer. And then in reality, since you have like neural net rather than a infinitely flexible fitting function, and actually finite training data, you get approximate results. But yeah, it's useful to do this by hand. And just
Sorry, what is
F is just a neural net.
Oh, and if the second half also F. Oh, sorry, that was mine.
Sorry, was this the confusing part?
A little bit.
Okay, so yeah, so F is a neural network now that takes as input X and Z. So it takes as input data parameter pair. If the input would be if data would be two-dimensional and parameter would be two-dimensional, then the neural network would be doing something like R to the 4 goes to R. It can be that the data is like a 10 by 10 or 100 by 100 image, right? Then you have 10,000 pixels, and you might have two parameters. Then suddenly you have 10,002 input parameters. So then it's a network that goes from 10,002 to R. So it's this combination of X and Z, of data and parameters, that is the input into the neural net. Time is almost up. Good. So let me first show you how to calculate them posterior then. So once you train a network like this, the posterior is just given for a specific observation by evaluating the prior times e to the power of f. And if everything goes well, this will be automatically kind of normalized to 1. Typically, it's not exactly normalized to 1, so you have to normalize it to 1 by hand. But this gives you then posterior samples. And the nice thing is this here works, as I said, with arbitrary network architecture, so there's a lot of flexibility from that side. There are then reasons why this doesn't work if you have high-dimensional data and high-dimensional parameters at the same time. But that's this algorithm, or this approach is the one that you see in the tutorial, actually. It was just easier to code up, and it's something that we use often in my group. So it's something that you will see there. Just as an example for how a network could look like. So we have now the problem, we need to define this network, right? Which takes as input some image, let's say, and parameters. So the way this usually works is you would first have an embedding network, let's say a convolutional neural net. Didn't really talk about how convolutional neural nets work, but let's say this is just a neural network that is optimized for image analysis. And this convolutional neural net would produce some data summaries. So it would take, let's say, a higher resolution image and compress it down to a vector with 10 components. And then we would have still our original parameters, and we would concatenate both into a new vector. How do I write this? SZ. Let's call this A or something. And then this newly concatenated vector would go into the network, or into a multi-layer perceptron. Which would then just go to R. So this would return the log ratio, or the thing that will turn into the log ratio in the end. So the structure that you also will see in the notebook is for one of the examples that are there. There's a little convolutional neural net that takes an input image, generates data summaries. Those are then concatenated with the parameters. This goes then into a little multi-layer perceptron, which essentially studies how the parameters are correlated. And then it returns this ratio. And if you go back to this ABC example, what this actually means is if one trains the entire thing, this CNN part would